Hey everyone, let's learn the material from Chapter 6, Discrete Probability Distributions. Now Section 6.1 is going to start off by talking about random variables in general. Section 6.2 deals with a specific discrete probability distribution, the binomial distribution. First, let's discuss some basic terminology. Remember that the distributions in Chapter 7, 8, 9, 10, and 11 are continuous distributions, right? Either the normal distribution or the student's t distribution. We're going to be looking at discrete probability distributions, things that you can list. And in particular, this was really our introduction to random variables in the book, right? Because Chapter 6 comes before all these other distributions. Okay? Now, recall that a variable is a characteristic whose label or value may, vary for different individuals. An experiment is a situation where unknown results occur. Each unknown result is a separate outcome. And the set of all outcomes is the sample space. So the sample space is a set of all the outcomes. A subset of the sample space is an event, right? Just a collection of outcomes. So for example 1, a poker player shuffles the 52-card deck and draws 5 cards to form a poker hand, right? So randomly drawing 5 cards. Describe both the experiment and sample space. Pause the video and take a minute. See if you can do it. Here's the answer. Experiment is the player randomly drawing 5 cards from a 52-card deck. That's the experiment, is the act of randomly drawing 5 cards. Okay? The sample space is the set of all 5-card poker hands. And by the way, if you're interested in counting them, if you want to know how many outcomes are in the sample space, it turns out you don't need to know this. This is just a little trivia tidbit. It turns out there are 52, choose 5, which is about 3 million outcomes or poker hands in the sample space. You don't need to know this. I'm just pointing out that the sample space can be quite large. Okay. A random variable is a, random outcome, not a random outcome, is a numerical of a random experiment. And I just want to point out that the book uses the word random experiment. The book talks only about random experiments, just so you know. So I define an experiment in general, but for our purposes, we're defining only random experiments, right? Where we're randomly selecting things, random variables, right? Discrete random variables, which is what we're interested in, can be listed. Continuous random variables can assume each or every value in an interval. Right, this goes back to Chapter 1 stuff when they define continuous and discrete variables, right? This week, right, for this lesson, we're going to focus again on discrete random variables, right? That's what Chapter 6 is all about. For continuous stuff, we look at Chapter 7, 8, 9, 10, 11, etc. All right. Now, let's consider an experiment where an individual flips a fair coin 3 times. Write a chart containing all possible outcomes and their probabilities. Pause the video and see if you can do it. Try to write them in order if you can, or in some kind of meaningful order. So let's do it. Now we're assuming that this is a fair, right? I say a fair coin, right? The flips are independent. I'll discuss that in a sec. right? So let's see what we have here. So the first outcome for me is, I would say HHH. You could have HH, right? So H is heads, T is tails, right? Now this is in a certain order, but if you're not ordering things the same way I am, then that's totally fine. 1, 2, 3, 4, 5, 6, 7, 8. Now I know that there are actually 8 outcomes. I listed them all. You can count them. But also, if each coin flip has 2 outcomes, then you know that 2 times 2 times 2 is 8, right? So there are 8 outcomes. So let me just put in parentheses here, 2 to the third equals 8 outcomes in the sample space. All right, okay. I don't really need that period there, do I? All right, anyway. So the probability for each of these, if you think about it, is just 1/8. Right? Each of them is equally likely. Now, one thing that we are assuming about the coin flips is that each coin flip is independent. And in general, 2 events, A and B, are independent if, here's some notation, the probability of A, if the probability of A and B, right, that's how we denote the probability of A and B, equals the probability of A times the probability of B. Okay, that's what it means for 2 events to be independent. Okay, now a probability distribution is a list of probabilities for each value of a random variable. Now, I'm going to introduce some more notation. First of all, just to be clear, I want to point out that you could write the probability of x means the probability that the random variable, I'll just say is x, right? That's one way you can do it. Actually, sorry, I guess I do it over here. Probability of x, so I guess I don't actually need this. Don't need that over there. Let p of x denote the probability of a random variable having the value x. Now, the other way that you could say this is you could say x is a random variable. And then you could say, because you sometimes see this in probability books, the probability that big X equals little x, denote the probability of a random variable big X having the value little x. I think it's a little confusing, but you might see both. Okay? Now, hopefully we all remember this from some point. The probability that a variable can, just the probability of anything, is always between 0 and 1. 0 means it never happens, 1 means it always happens. Okay? And if a random variable big X can, if this, let me put it this way. If the set x1 through xn, if that's our sample space, then the probability that x assumes x1 or x2 or x3, etc., is 1. Okay? So for our next example, if we reference example 2, find the probability that we flip a coin 3 times and get at least 1 heads, or at most 1 tails, or etc. Pause the video, see if you can do these. Here we go. So I'll write this as the probability of at least 1 heads equals, well, if I just go and look, every one of these options has at least 1 heads except the last one, right? So that's going to be 7 outcomes where it happens, divided by the total of number of outcomes in the sample space. So that's 7/8. The probability that we have at most 1 tails, well, let's see. We're looking for no more than 1 tails. We have these guys and this guy. Looks like 4 out of 8. Let me make this a little bit. Probability of exactly 2 heads? Well, again, we just count, right? Here are 2 heads, here are 2 heads, here are 2 heads. 3 out of 8. Notice that we're always dividing by the number of elements in our sample space, right? The total number of outcomes, right? The probability of an event is, let me just write this down here, right? The probability of an event equals number of outcomes in the event divided by number of outcomes in the sample space. Okay. So the probability of getting exactly 2 tails, well, whatever it is, it's going to be divided by 8, right? Because that's our number of elements in our sample space. Well, there's no difference between heads and tails. I shouldn't really even need to look, right? It's totally symmetric. It should be 3 out of 8. And then the probability of at least 3 tails, well, how often do we have 3 tails? It's just that one time. So, right, it's 1/8. Okay? So that's what we get. Right, and note that the events 2 heads and 2 tails are what we call mutually exclusive. Which means they can't both happen at the same time. Right? So in general, events A and B are mutually exclusive if the probability of A or B equals the probability of A plus the probability of B. Okay. Also, 2 events, I'll call them A and B, are complements, not complements. We're not saying something nice. We're completing, comple, right? If A or B equals the sample space, right? i.e., if probability of A, maybe I'll say plus the probability of B equals 1. Or probability of A equals 1 minus the probability of B, right? I hope you see that those two statements are the same. Okay, now just pause and describe two events that are complements, and if possible, then state their probabilities, just to check. So here's an example. We will say that at least 1 heads and 3 tails are complements. Right? Not only they're mutually exclusive, right? They're complements. Probability of at least 1 heads is 7/8. Probability of 3 tails equals 1/8. So the probability of of at least 1 heads plus the probability of 3 tails equals 1/8 plus 7/8, which equals 1. So sure enough, they are complements. Okay. That's all for the first video.